How's it going, everyone? In today's video, we're going to go through 10 fundamental Python concepts that form the foundation of almost everything you'll build as a programmer. These are not just random features of Python. They are the core ideas that determine how you structure code, store data, organize logic, and build real applications. If you understand these properly, everything else in Python becomes significantly easier to learn. So with that in mind, let's start from the very beginning. Before you write any Python code, you need a place for it to live. That place is a Python file, which uses by extension. For example, if you create a file called main.py, you are telling the operating system and Python interpreter that this file contains Python instructions. When you run this file, Python doesn't execute everything at once like a compiled program. Instead, it uses an interpreter, which reads the file line by line and executes each instruction in sequence. This is important because Python is highly dynamic. It allows you to test, modify, and run code very quickly without needing a separate build step. So every Python program, no matter how complex, always starts with a simple single quotes .py file. Now let's talk about variables. A variable is one of the most important concepts in programming because it allows you to store and reuse information. Instead of repeating values everywhere in your code, you store them once in memory under a name. For example, if you write name equals Bob and age equals 20, you are telling Python, keep these values, and let me refer to them later using these names. What's actually happening behind the scenes is that Python stores these values in memory, and the variable name acts like a label pointing to that memory location. So whenever you use name, Python retrieves the stored value instead of asking you to type it again. This makes your code not only shorter, but also much easier to update. If Bob's age changes, you only change it in one place instead of multiple places. Now let's go deeper into data types. Every value in Python has a type, and that type determines what you can do with it. Integers are whole numbers. They are used for counting, indexing, and mathematical operations. Floats represent decimal numbers. They are useful when precision is needed, such as measurements or financial calculations. Strings represent text. Even though they look simple, strings are powerful because they allow manipulation of text data, formatting, and communication with users. Booleans represent logical states. They are the foundation of decision-making in code. Every condition in Python eventually resolves to either true or false. Now things get more interesting with collections. Lists are ordered collections of items. They are flexible and can grow or shrink dynamically. This makes them useful for storing things like user data, items in a shopping cart, or results from computations. Tuples are similar to lists, but they are immutable. This means once created, they cannot be changed. This makes them useful when you want to protect data from accidental modification. Sets are collections of unique values. They automatically remove duplicates, making them useful when you care about uniqueness rather than order. Dictionaries store data in key-value pairs. Instead of accessing data by position, you access it by meaning. For example, instead of first item, you might use a key like name or age. Together, these data types form the foundation of how Python handles and organizes information. Now let's talk about type annotations. At first glance, they might seem unnecessary because Python is dynamically typed. That means you don't have to declare types explicitly. However, as programs grow larger, this flexibility can become a problem. Type annotations allow you to explicitly say what type of variable should be. For example, you can specify that name should always be a string, and age should always be an integer. Even though Python will not enforce this at runtime, tools like code editors, linters, and type checkers can use this information to catch mistakes early. This becomes extremely useful in large code bases or team projects where multiple people are working on the same system. Think of type annotations as guidance for both humans and tools. They don't control execution, but they improve clarity, reduce bugs, and make your code more predictable. Now, let's move on to constants. In theory, a constant is a value that should never change once it is defined. Python, however, does not strictly enforce constants like some other languages do. Instead, it relies on convention. By writing variable names in uppercase and optionally using the final type, you are signaling to other developers that this value is meant to stay unchanged. For example, a version number or a mathematical constant like pi should remain stable throughout the program. Even though Python won't stop you from modifying it, the purpose of constants is not enforcement, it's communication. They tell other developers, do not change this value unless you really know what you're doing. In larger systems, this helps prevent accidental bugs and improves readability. Now we reach one of the most important concepts in all of a function is a reusable block of code that performs a specific task. Instead of writing the same logic multiple times, you define it once and reuse it whenever needed. This is extremely important because real-world programs often involve repeated actions like formatting text, processing data, or performing calculations. Functions also help organize your code into logical blocks. Instead of one large, messy file, you break your program into smaller, manageable pieces. Functions can also take inputs, called parameters. This allows them to behave differently depending on what data you give them. For example, a greeting function can greet different users depending on the name passed in. Additionally, functions can return values. This means they don't just perform actions, they can also produce results that can be used elsewhere in your program. This combination of input, processing, and output is what makes functions so powerful. Now we move into object-oriented programming, starting with classes. A class is essentially a blueprint or template for creating objects. Think of it like a design plan. The class defines what something should have and what it should do, but it is not the actual thing itself. For example, a car class defines what a car is in general, its properties like color and horsepower, and its behaviors like driving. Once you have a class, you can create multiple objects from it. Each object is a separate instance with its own data. This is extremely useful because instead of rewriting code for every object, you define it once and reuse it as many times as needed. Classes help you model real-world systems in a structured and organized way. Inside a class, the initializer plays a critical role. The initializer is a special method that runs automatically when a new object is created. Its job is to set up the initial state of the object. For example, when you create a car, you might want to immediately assign its color and horsepower. Instead of manually setting these values after creating the object, the initializer handles everything in one step. The self keyword is important here because it refers to the specific instance being created. This allows each object to store its own unique data, while still using the same class structure. Without initializers, object creation would be repetitive and error. Now let's talk about methods. Methods are functions that belong to a class. They define what an object can do. If a class defines what something is, methods define what it can do. For example, a car object might have a drive method that prints or simulates movement, or a method that displays its details. Methods use self to access the object's own data, which means they can behave differently depending on the specific instance. This is what makes object-oriented programming powerful. Data and behavior are combined into a single structure. So instead of just storing information, objects can actively perform actions based on that information. Finally, we have dunder methods. Dunder stands for double underscore, And these are special methods that allow you to customize how Python behaves with your objects. Normally, if you print an object, Python shows a generic memory reference, which is not very useful. But with a string dunder method, you can define exactly how the object should be displayed. This makes your objects more readable and meaningful. Even more powerful, dunder methods allow you to define how operators work with your objects. For example, you can define what it means to add two objects together using the plus operator. This gives you complete control over how your custom objects behave in Python expressions. In short, dunder methods allow your classes to integrate seamlessly into Python's built-in behavior system. And that brings us to the end of these 10 Python concepts. We started with the basics, like files, variables, and data types, and moved into more advanced topics like functions, classes, and dunder methods. Each of these concepts builds on the others, and together they form the foundation of Python programming. The most important thing now is practice. The more you write code, the more natural these ideas will become. If you found this helpful, don't forget to like and subscribe so you won't miss the next one. It really helps to support the content, and let me know if you want more videos like this. Thanks for watching, and I'll see you in the next video.